Okay, we're going to make a slight pivot. I mean, the whole morning and afternoon you've heard a lot about generative AI and LLMs. We're going to pivot to quantum computing, and I've got three wonderful panelists to talk about it. So please welcome Jack, and Christine, and Stratton.
Thank you.
Great. So I thought, since this topic is somewhat different, and it would be good to have Jack start off with a few slides in terms of setting the context around quantum computing, and then we'll get into questions.
Just need our clicker. Thanks. Great. Well, thanks, Mandeep, for having us, and thanks to the Evident AI. Maybe I'll stand over here so I don't block anybody. And I think what's exciting is AI is right now in people's minds. We're all talking about LLMs, but there is a world beyond LLMs. Yes, it does exist. And we are here, the three of us plus Mandeep, are here to tell you about this world. Thank you very much. So, great. Just make sure this is moving. Oh, let me go back one. Let's see if this starts. And it.
I'm a mathematician, so I can't tell a funny joke.
That's okay. Anyway. Let's see. Okay, here we go. Great. So, just to recap, you heard about LLMs today, neural networks inspired by the brain. We have 80 to 100 billion neurons in our brain. Any guesses how many synapses we have in the average brain? How many connections we have in the average brain? I'll start the bidding at 1 trillion. Any guesses? How many connections in the average human brain? 100 trillion? Any other guesses? We have one bold guesser? 50 trillion. So it's anywhere between 100 trillion and 1,000 trillion, right? We actually don't know the exact number. We don't have a computer on Earth that can even simulate that one brain, let alone many brains. And of course, based on this, deep learning has been around for a long time now. Jeff Hinton, Yoshua Bengio, Jan LeCun, many others really pioneered this field. Inspiration. 2017, the paper Attention is All You Need really focused us on how we can parallelize some of these operations using GPUs. And of course, now we're here with LLMs today. But let's go now to the next step. These GPUs, initially the G in GPU, of course, for graphics, and you see the wonderful graphics of video games. When you see a teenager, thank the teenager for playing video games, because that's why we have these GPUs today. And they are good for deep learning. But now, part of what we're here to tell you today, the four of us on stage, is there's now use cases for GPUs beyond LLMs, specifically to do physics calculations. In combination with QPUs, we're going to hear about quantum computers, GPUs can now start to run quantum equations at scale. This means molecules, it means drug discovery, it means chemicals, but also for those of us in this room, focus on the finance sector, it means high-dimensional risk management. It means portfolio optimization. These are higher dimensional tools than Monte Carlo and traditional tools that we had. This is a different complementary use of GPUs than just LLMs. We're going to be talking about that today. Let me talk a little bit about just pharma in terms of we know the stats, the horrible stats in the pharma industry. We know it takes 14 years on average to get one molecule to become a drug. We know it takes about $2.5 to $3 billion. We know the failure rate in clinical trials. Any guesses on the failure rate? I'll start the bidding at a 50% failure rate. Any other guesses? 80%. 90. So it's about 80 to 90% failure rate. 1 out of 10 make it through. And that 1 out of 10, of course, has to pay for all the losses, which is why we have a lot of high prices for drugs as well. How can we change that? Now, LLMs, maybe some role there in terms of looking at some literature, but you can't ask an LLM for a molecular formula, you'll get a hallucination. If it was in the literature, we actually would have made that drug already. What you can do is use the tool sets that we're going to be talking about here today, the algorithms, the hardware, the software, the integration, to actually do drug discovery in a completely different way. To actually use first principles physics, do the molecular work, and then apply AI to that new synthetic data. Data is where it's at, and it's not just data that you find on the web. In the case of those of us on this stage here, we create new data sets. We use physics to do that. And now let me hit one other use case before we start the panel, which is battery chemistry. We're all excited about electric vehicles. We're all excited about clean energy. we have to store that clean energy somewhere, and that means batteries. Lithium-ion batteries have been around for 40 years. They're getting about 4% better per year, every single year. Not exactly Moore's Law. And also, lithium has major supply chain issues. Right now, 75% of all the lithium in the world is processed in one country for batteries. Any guesses which country that is?
China.
Yes, good. Very, very good audience here. And so what you have is a supply chain choke point. How do we get beyond that? What you see on this animation is that of the 118 elements, there's about 19 that you can make a battery from. The anode, the cathode, the electrolyte, the membrane. That's 10 to the 117 possible combinations. There's no physical way to build all those prototypes, but now using the tool sets that we're going to talk about here, we can make those breakthroughs. And then finally, in financial services, as we'll hear discuss, there are many applications in portfolio optimization and in risk management and risk analysis that we can now explore using this hybridized tool set of quantum processors and GPUs using these new kinds of algos. So AI and LLMs, great, but simulation and all these other types of tools also very important. In financial services particularly, a lot of very interesting computational capabilities that are now just being explored by the banks around the world. There are prototypes, there are tests happening right now at some of the banks represented in this room, and banks also around the world. This is something we'll get into a discussion on. And of course, we'll also discuss the threats. AI and quantum, people have been talking about now the AI threat exterminating humanity. Not sure that's going to happen, but I can tell you that because they can penetrate into the firewalls much easier doing that, and the vulnerabilities get exposed. We have to now move to a zero trust architecture. There was just a big breach yesterday by one of the big password managing companies out there because they assumed their firewall would actually protect them, but in fact it didn't. And a file with 100+ million customer records got exposed. Now every file has to be protected. We'll talk about what cybersecurity means in the age of AI and quantum. And finally, here are some questions just to think about. As you think about your portfolio of public listed companies, you think about asking management questions. Are they using AI? Are they using quantum? We have to go deeper in terms of the use cases. Sure, we can use LLMs to reduce customer service call costs. We can use LLMs to drive marketing and in a better, more efficient way. Those are more superficial cases. What we're going to talk about on stage is deeper use cases that drive the core innovation of the company itself. Thank you very much.
Great, thanks. And that was quite a bit, in terms of the slides and the content you showed. So clearly a little overwhelming. But I want to push back a little bit, on what you said around.
Want to provocative.
Yes.
Said be provocative. So we're trying to get this conversation going.
And I would appreciate if there are provocative audience questions as well. So get ready for that. But maybe to start off the discussion, help us understand. How do companies actually make that leap into quantum? I mean, we have seen how generative AI came to the scene. First there was training, now we're talking about inferencing more and more. Help us kind of understand the stack and the prerequisites for quantum computing.
Yeah, let me start off and then let me turn to my co-panelists as well. The first message is that quantum is not just about computing, right? So there's quantum sensing, there's quantum communications, there's many, many aspects of quantum. To give one example of quantum sensing first, if you think about Airbus, if you think about Boeing, if you think about Delta, BA, any of the big airlines, or in fact the US Air Force or the Royal Air Force, all these different companies depend on one particular technology, navigation. And today, all of us in our phones, we navigate with GPS. But what if you didn't have GPS? What if GPS was jammed? What if, as of right now, happening right now over certain parts of the world, GPS is being spoofed? That's even more dangerous than being jammed because now your plane, traveling at 500 miles an hour, is getting the wrong GPS signal. A GPS signal that it thinks is correct, but now you're actually veering off into the wrong space. 4 planes veered off into Iranian airspace just 6 weeks ago because they got spoofed GPS signal. It's public, it's online, you can check it out. Pilots now in that general area have to watch out for being spoofed. Quantum sensors give us the ability for the first time to navigate without GPS, to navigate the way birds and whales do, with the magnetic field of the Earth. And what enabled that? What enabled that was the quantum sensor to detect the magnetic field, a GPU, the ones we just discussed here, and most importantly, an AI model that can distinguish between that magnetic field and an iPhone or some other magnetic field around the plane. So quantum sensing is something here today. It's right now here today. When it comes to computing, what's nice about computing is we can look at a hybridized future. One where you use GPUs right now, like as we're describing here, and then as the quantum computing folks like PsiQuantum so expertly start scaling up the number of qubits, the error correction, you can start to hybridize the GPUs and the quantum processors, the QPUs. The algos can be designed today to run on both platforms, so we can have a hybridized kind of future. So I don't know if my co-panelists want to add to that, please.
One of the things that we did together was around portfolio optimization. So this is a banking crowd, and one of the things that we did was we were able to take this hybridized environment, and we were able to simulate quantum optimization for a whole portfolio. And we were able to include more variables than what we could in a classical environment. We were able to use sustainability along with your typical risk factors and really create this optimized portfolio for investors to look at and propose for their clientele.
But you can't do that with traditional CPU architecture or the way things are done. So what's special about doing it with quantum?
Yeah, so one of the things that is exciting is that we're not quite there yet when it comes to quantum computing. So to solve a net new algorithm or a net new problem, that's the promise of quantum computing. And because we're not there doesn't mean that it's irrelevant. So we need to practice. We need to get that muscle memory going. And so what we're doing is creating that muscle memory. And we're able to now achieve what we call quantum utility, where we're able to get a real result out of quantum hardware. And that's exciting because that's something we weren't able to do just 6 months ago.
So Stratton, I almost thought like we were in a big data center super cycle because of what's going on with the world of generative AI. Where do you fit in, given you're a hardware-focused company on quantum?
Yeah. So PsiQuantum is very different and contrarian than any of the other quantum hardware vendors that you've probably heard of. From day one, we decided we needed to build a fault-tolerant, error-corrected, utility-scale quantum computer. It's going to be big. It's going to fill the same size and space as a new AWS kind of data center. And we think the algorithms being written today for the disk machines are absolutely useless, and you will not be able to step up and take those into the fault-tolerant realm. So when we think about the algorithm development and teaching your teams what to do, it's a different world to develop a fault-tolerant quantum algorithm that uses all of the entanglement and the superposition capabilities, and then will give you, useful results. We think that has to be 1 million qubits or more, fully error-corrected, and written with software tools that understand the architecture's fault tolerance capabilities and error correction codes. So it's a contrarian view. We've been doing that since day one, and we will never build a demo machine or a small machine. You'll see our first machines appear very soon, and in a way that the way that we break through all of the technology pieces, we use traditional semiconductor manufacturing. We're at a global foundries in New York, makes all of our chips. We use traditional fiber connectivity and photonics chipsets. We are now building cabinets for our blade servers. So when you design a new computer system, you design it by saying, what does it need to be? What is the endpoint? And then you get all the things that you have to innovate with done. You innovate where you must, and you borrow where you can. And we've borrowed everything from semiconductor technology to photonic technology on the ramp. So that's why we think the world needs to start thinking about fault tolerance. So stochastic modeling is obviously one of the big things that you all deal with in financial services. It's the modeling on Monte Carlo and the rest. You're going to need millions of gates and millions of qubits to do anything interesting, right, that will give you derivative pricing that is actually worthwhile and truthful advantage for the business. So I worry, right, that we're not training, right, inside and outside enough people on how to start thinking about this differently, right, about these big architectures. You're going to have error correction and tool sets. Now, we'll give you a Python interface. That's not going to get you very far. You're going to have to learn about circuit diagrams and gate depths and fusion and all kinds of things. So One of the things we do webinars with Jack and his team, and we want to start pushing education more, and even going into the universities and starting to push curriculum on this. They're not graduating enough what I think are quantum savvy developers.
Can you talk about education now?
Yeah, I mean, look, one of the hard parts about kind of driving commercial adoption for any new technology is how do you educate people? And in this case, I think the reason why Gen AI really took off is because OpenAI came up with a chat interface, made it easy for user to play around with it. So is there an equivalent that is coming around quantum as well?
Chat qubit, yes.
Yes.
It's exciting. I think the education piece is a big one, and one of the things that the three of us talk about and our industry talks about is the quantum divide. We all know about the digital divide 20 years ago. Bloomberg, Gartner, and others talked about how there were the haves and have-nots in terms of access to smartphones and applications and so on and so forth. Finally, that's now closing. We're seeing 300 million people who never run the internet join the internet every quarter. Every 3 months, 300 million net new people join the internet. Within about 4 years from now, we'll have basically closed the entire digital divide. However, now the quantum divide is opening. So there's about 20 countries, US, UK, Germany, France, Australia, a handful of countries that have strong quantum programs. China, very, very strong. We'll talk about that. But 180 countries don't.
Yeah.
And so how do we start to nip that divide in the bud rather than letting it grow and grow? And part of that is education.
Yeah, and even with advanced computing, with generative AI, only 30% of the world has access to advanced computing.
Yeah.
It's not enough.
So to me, LLMs actually are part of the solution here. One of the beauty things about LLMs is as an AI tutor, as an AI educator. And so a number of us, you'll see coming out over the next 3 months jointly with a number of LLMs basically that are training people in the quantum programming. As Stratton just correctly pointed out, programming for a quantum computer is a very different kind of thing. It's not just the kind of code that you're used to. The gates are different, the operations are different. It's a very different way of computing. It's very, very powerful and efficient. 10 lines of code for a quantum computer can do a lot compared to a traditional computer. But Mandeep, we really need to think about this education piece, democratizing it. The fear that a lot of us have, that if we don't do this, that it's really going to be as big a divide as the digital divide. The good news is that at the WEF, at the World Economic Forum, at other venues, we're all starting to really talk about it, try to bring this, close it in.
So let me push back a little bit even on that point. I guess one of the things, at least from our perspective, why Gen AI adoption has taken off so quickly is because things are being done on the cloud. And everything is abstracted. You can start an instance easily on one of the hyperscale clouds. How do you kind of help an industry that's predominantly on-premise? I mean, let's talk about banking here. Most of their workloads are still on-premise. The critical systems are being run on mainframe. How do you have them transition over to something as new and as risky as quantum?
Well, Gen AI is helping this narrative. We heard today a lot about the AI first principle. And so I think we are starting to move more as an industry towards the cloud. We're going to see a lot more of that adoption. And then in the era of quantum, we're going to see this hybrid infrastructure where you're going to access quantum computers through the cloud, just as you are still going to be accessing your...
I mean, right now the hyperscalers say they are capacity constrained on the GPU side. Nobody has said they're constrained in terms of the quantum capacity. So obviously...
So you say it's scary, quantum scary, and risky.
Yeah.
I'd be scared not to do this.
That's right.
We expect there to be, we will be first, and we expect there will be a scarcity of time and capacity on the systems. Right? And there's just so many use cases and these are, if you have a tractable problem that you can already run today, it's not a quantum problem. We only like intractable problems, the ones you can't run. Those are the ones that need to get figured out, and whether it's derivative pricing or optimization in your industry, or it's drug discovery, we all said the drug discovery, battery chemistry, all the same things. These are the hard problems that quantum can solve. We don't want the easy ones. We don't want polynomial. Right? We don't want quadratic, or we want exponential improvement over what you can do. We've done one for elliptic curve cryptography and code breaking, 700 times faster in our latest instantiation, which means you can go from 3 trillion years to break it to 9 minutes.
Yeah. Just one point on data. For financial service folks in the room, data is everything. Banks run on data, hedge funds run on data, buy side, sell side, we all run on data. And again, in the deep learning context, in the context of LLMs, we're used to having a lot of data in front of us and then training a model, a brain-inspired model, to go and find patterns in there and then make predictions or output. But in many cases, particularly in financial services, we have to actually create new data sets. And that's again, that's again where the cloud-based infrastructure is really helpful. Having GPUs and then quantum processors on the cloud let us create new kinds of data sets using superposition and entanglement that we can never create before. So when people think about the models of the future, the AI models of the future, the question I have for you is, where is your data coming from? Your model's only good as the data you put in. And we have to start getting used to thinking not just getting data from various parts of my bank, but actually creating new data sets. Well, you just brought up cybersecurity, so I think we should maybe talk about that.
Let me say one thing. Guess where the data is not going to be stored? On the quantum computer.
Yeah.
There is no storage, right? So you have to have this hybrid model in and a hybrid model out.
Yeah.
Right? And we will do all the analytics and give the answers and then pass off to the...
I mean, again, not to be a skeptic here, but when I look around myself, there are lots of smartphones, PCs, traditional CPU servers. The install base is overwhelmingly, skewed towards the traditional compute architecture, and now with GPUs. Like, how do you see people actually bringing quantum into their day-to-day life? Or this is more of a nuanced use case for risk management or for, fraud detection, those
I wouldn't
type
call
of
it a
things?
nuance. This is a big B2B use case. I'm not sure most consumers will be directly doing chat qubit with a quantum computer, but there's going to be a lot of big B2B use cases. In fact, what we expect is that most of the large business of the world will be using quantum, again, though, hand in hand with traditional architecture. So quantum doesn't replace old computers, classical computers. It is a side-by-side interaction.
Well,
synergy.
this is your new generation of HPC, right?
Yeah.
It's not, so how is it going to impact the consumer? Because those drugs may get to market, in 3 years instead of 7, and because there's so much less failure and so much more confidence in what's coming out of the analysis, then drug prices should go down. That's what a consumer will see.
Yeah.
But the big breakthrough that came with neural nets and LLMs was how I guess certain number of researchers arrived at a large language model and really figured out what the parameter rate should be. Do you think we are waiting for that kind of a breakthrough, even with quantum computing, where somebody needs to figure out, okay, this is a model that works with the right kind of weights and parameters, whether it's trillions of parameters or, and just to draw an analogy here, are we waiting for that moment, or you think that moment is already here?
We're certainly waiting for the hardware, the quantum hardware to be at a point where we can run these net new algorithms against it. That is the tipping point that we're waiting for.
So did your life get better because AlphaGo beat the Go champion? These are these aha moments that you have with some of these technologies where that Sycamore, Google's quantum computer, can compute a mainframe. So what? There's nothing that got added to society because of that. So I think quantum's going to be very much different. It's going to be transformative. It's making possible what is today impossible. And the breakthroughs are going to come when the hardware's there and the algorithms are developed, and you push a button and that project runs in whatever amount of time it takes, and you will get a breakthrough answer on the problem set you've come to. I am more confident than that than I've been in anything in my 40 years in tech.
So Jack, something that you and I often talk about when we're on stage together, I think maybe I should talk about the two promises of quantum, because we kind of skipped over that, but just for the audience. There's two promises. The first one is that quantum is going to give you something net new. So today, 2 + 2 is 4 in a classical environment. But in a quantum computer, 2 + 2 has the probability of being pink. It's going to give you something unexpected. It's just you weren't prepared for that, right? And then the second promise of quantum is that it's going to speed things up. And speed isn't always faster. Speed in quantum is going to be net new revelation. It's going to give you a solution to something. So part of the research that Jack and I did with a client was drug discovery. And exactly what we've been talking about was what kind of net new molecule can we create that helps shorten that lag time and shorten the false positive rate. And then we were able to take that same use case and apply it to banking for fraud detection, so that now we can find that anomaly in the haystack faster, better, smarter. So there's combination of those two promises that gets us super excited about quantum, and why all of you should be really, really excited about that. But we're not there yet.
Yeah.
We need the hardware to arrive.
And look,
Always my fault. There's no hardware. Okay, I get it.
Mandeep, I want to come back
Yeah.
to the original question of how do people prepare for quantum? Because quantum giveth, but quantum also taketh, right? In the sense that there's a lot of positive things, transformative things that are going to happen because of quantum. We have no doubt about that. But one thing for sure that's going to happen, current cryptography, current public key security goes away. So everyone's phone here, when you have WhatsApp and it says end-to-end encrypted, that is breaking. That is going to break once you have scaled, fault-tolerant quantum computers. The elliptic curve that Shran just mentioned, broken under scaled quantum computers. The entire financial services industry, the whole banking system, is built on public key cryptography, on RSA, elliptic curve, and these similar type of algorithms. All that has to change. So the answer is, how do you prepare for that? It takes banks, on average, 10 years to get to a new standard.
Yep.
So we can argue maybe offline which year exactly we're going to break all these big cryptography protocols, but I can tell you it's within the time frame that it takes banks to actually move over. And because of that, what the major banks are doing now is they're starting their cryptographic inventory. They're actually deploying software and saying, what cryptography are we using where in our bank? Doing the triage, doing the analysis, and saying, how can we now take the most sensitive of this data and move it to the new quantum-resistant algorithms, the algorithms that will actually withstand the attack of the quantum computers. And that's very important because, the entire infrastructure, the SWIFT system, the ACH system, everything we know in banking, every trade you do on the markets desk is dependent on public key cryptography. All that has to now be changed.
Well, you may not know this, but I was the founding CEO at VeriSign.
That's right.
We put all the PKI in, and he's exactly right.
Now we got to redo.
We've been waiting for the day. Now, by the way, every 10 years we say, oh, it's coming soon, and it hasn't come. And it's because there isn't enough power to do it. And the trick that we all have used is we'll just increase the key size. We just keep increasing key sizes.
in fact, that's a perfect segue into the ecosystem and standards kind of question, which comes up with any new technology. How do you go about building an ecosystem for something like this? And do you have a vertical focus strategy, or you kind of get together the way you guys have done it? I mean, what's the
It
approach
definitely
here?
takes partnerships. I mean, all three of us are partnered on this stage, and we were not selected because the three of us have partnerships. But we have partnerships with everyone. PsiQuantum has many partnerships. EY has tons of partnerships. We have to build this ecosystem and build the mesh of this ecosystem. Key stakeholders include academics.
Yes.
At Sandbox, we're working with 43 universities. Mariana is here, a PhD, who's heading up our university relations. So we're working with universities here. Big news for New York City. NYU just announced that you can now have a minor in quantum technology at NYU, just announced just a few days ago. So the university sector is very important. The government sector, also really important. Talking about standardization, NIST, the National Institute for Standard Technology that we all work with, played a fundamental role. It's not every day you can say, hey, government, you did a good job. But in case of NIST, they actually did. 7 years ago, NIST said, let's have a protocols contest for what protocol would replace the current RSA, the current public key protocols that you did so much to actually put in place many years ago. And in fact, many submissions came in, a really good process that was very transparent ensued, and now, as of July 5th last year, we now have that set of new protocols that are moving through final standardization. We expect that to be Q3 of next year, around 1 year from today, to have the finalized standards and protocols that we will all move to for quantum safety and encryption.
Congress should be passing the Quantum Initiative Act any moment, second,
Any day
day
now.
now.
Yeah.
And DARPA has been running a utility-scale quantum computing validation for the last year. PsiQuantum, Microsoft Atom Computing were involved. We've been told we've actually graduated to the second phase, which will begin in January. So the government, specifically related to the DoD, because of both the China situation and this COVID, very, very on top of this now, and there's a lot more effort than there was even a year ago from DOE, Department of Commerce, Congress, and the DoD in all of this. So public-private partnership in quantum is going to be key to the U.S. and or our allies staying ahead if you forgive it, the curve here relative to China. We don't know what China's working on. We don't know how many people they have working on it. But the estimate is about $15 billion worth of spend.
Billion.
The billion, and the next closest that we know of is probably 5 billion US, and then it goes to $1.5 billion in the UK. It pales in comparison.
Yeah. Part of this ecosystem also, Mandeep, is the quantum networking. JP Morgan announced publicly, so we can talk about it, a quantum networking experiment they did with Toshiba. Others will be announced in the next 3-4 months. Why is quantum networking important? It's important because there's multiple ways to connect quantum computers and quantum sensors together. Today, of course, we're going to do that with the classical internet, right? The current TCP/IP internet that we're all familiar with today. You'll access a site quantum computer, you'll give it a job to do, it'll give you a response, classical information, you'll then move on and then use that response to get your work done. However, there's another way that, particularly for science and ultimately for banking as well, will be very interesting, is to take two quantum computers in two different places and connect them coherently. Coherently is fun quantum jargon for actually keeping these very, very sensitive quantum states of superposition and entanglement. And this DQC, this is a fun acronym you can impress your friends with at cocktail parties. DQC, Distributed Quantum Computing, is going to be part of our future. Will it take 5, 10, 15 years? Yes. But this is going to be a future where you can take quantum sensors, the one I mentioned before, for your heart, for navigation, for others, and then connect them over a new parallel internet to quantum computers for direct processing. So it'll be over the current internet that you access, site quantum and other quantum computers, but eventually there'll be an ecosystem of players just like DARPANET, ARPANET, Internet, rose up over the last 60 years. We'll see the rise of new internet.
This reminds me of the metaverse. Back in 2021, it was like that was the rage. Everyone was so excited about the metaverse, and we know that didn't pan out the way everyone expected. So, what is it that could go wrong in your assumptions? Obviously there is a lot to talk about from a technology perspective, but I think maybe Christine, that's something you can highlight in your conversations. What are the factors that I guess clients look at?
I think thinking of this in silos is where we could go wrong. And so if we're waiting on the quantum hardware to reach a point where we can break cryptography, I think we're failing. Because there's going to be a combination of AI with the lesser state of quantum computing that can break cryptography. So we don't need to be thinking of this as a problem of only when a quantum computer is strong enough to break it in and of itself.
This week I heard, Jensen, I think he said all the software that will be developed from now on the development will be driven by AI, both on the software side as well as on the chip side. So it becomes a feedback loop. You're making better chips because you've got AI, and that's helping kind of feed on itself.
Absolutely.
Do you think there is potential for that kind of a flywheel to happen on the quantum side?
Absolutely. And I think that's why we are trying to partner with semiconductor industry now, so that we're
Absolutely. We have to do co-design, right? So we announced a partnership with NVIDIA. NVIDIA's made a lot of other announcements as well on their own in terms of their internal development. But why are we partnering with NVIDIA? Because we have to make sure co-design happens. When you look at CUDA, CUDA is that language that sits above the GPU chip, and between that and the application layer. It's important that that CUDA language speak our language. And that's why this co-design means when you develop hardware and software. The same thing with Site Quantum.
But it took so many years to develop CUDA. CUDA didn't come overnight. It took years of development on the software side.
And the same thing here. Again, all of those in responsible leadership positions in this industry always caution, this is not an overnight kind of ballgame, right? All of us on this stage and in many venues caution people, this is something to prepare for now, because again, it takes a long time to prepare for this.
Right.
But over the next years, not months, but years, this is going to start to impact you.
When we started the company in 2016, 17, we knew it would take a decade to build the machine, right? And we had very courageous and brave, venture capital investors, and since then, BlackRock and other folks who put in. But it's not a short game, and it's not a cheap game, right? We've also raised over $700 million, and we'll have to do that again here over the course of the next few years to finish what I keep talking about, and getting that machine to market and available to others.
So undoubtedly is a long game, But what's really exciting is a year ago when Jack and I started working together, we didn't expect to see quantum utility that year.
Yeah, yeah.
But fast forward 6 months, we worked on algorithms that were getting quantum utility. Quantum utility being, I could run an algorithm and it gives you a business productive result. It's not better, it's not advantage, so it's not better than what you could get out of a classical environment, but it's utility. And that's something we wouldn't have expected a year ago. So we are seeing these leaps sooner than what we would have expected.
If I could just jump on what Kristen also Stratton just said, deep tech or frontier tech is an asset class, an investable asset class. That's something we hadn't seen before, right? You talked about 2016 when Jeremy and Peter and yourself started PsiQuantum. That was kind of a new idea that as a venture investor, you'd invest in something that would take that long. Biotech kind of had that a little bit, but in IT, we weren't really used to that. We're used to an MVP within 3 months, get out your MVP, get customer feedback, start scaling immediately. We want to see 600 million users within 60 days. Well, when you come to deep tech, then you have to really think a little differently. Now here's what T. Rowe Price. T. Rowe Price now has a portfolio. They're a $2.1 trillion asset manager that's now invested more than $55 billion into deep tech companies. Not shallow tech, not light tech, but deep tech companies. Long horizon.
Space, rockets, nuclear fusion, and quantum computing.
Yeah. And so why is T. Rowe Price doing that? Because they know that, oh yes, it does take a little longer to do deep tech, but then you have a deep moat around the castle.
But
you have deep IP.
On the tech side, if I think in terms of stack, right? So there's hardware, there is data, there is distribution and algorithms. Where exactly in the stack are companies looking to invest? I mean, T. Rowe investing or somebody else looking to invest. What is it that they're focused on right now in terms of the potential?
Yeah, the good news is they're really looking at the whole ecosystem. So a lot of good investment is going into PsiQuantum and other hardware providers. That's critical. And then also a lot of investment is going into the algo providers, software providers. And then investment on the part of the large integrators. And it's not venture capital investment. EY doesn't need venture capital investment, already a scale company. But EY has to make the investment decision internally, right? To say, hey, let's hire someone like Kristen, somebody who's knowledgeable in quantum. Let's dedicate a team to this. And we're seeing that happen. So it's really, what's good news, the only area that I think is underinvested, to answer your question, is the quantum networking side. Yes, it takes a long time, but I don't see enough. There's a few startups. There's QNect in Brooklyn. It's a spin out of Stony Brook. We made a very small investment in that one. There's Evolution Q out of University of Waterloo in Canada. There's QFox in Delft in the Netherlands. So there's a handful, but they're not attracting the amount of capital, I think, that is deserving of that particular part of the ecosystem.
Okay. Let me see if there are any audience questions, please.
Any brave audience members?
Yeah.
Hi, I have a question. I'm Kevin Allison with Minerva.
Hi.
I wanted to talk about the getting to a commercially viable stack, because it feels like if we're talking about the finance sector or pharmaceutical sector, whichever sector, for it to go beyond just being an interesting kind of exercise in sort of horizon scanning or probing potential future use cases, you really do need a commercially viable hardware component, or to really go at enterprise scale. How far away do you think we are from that? I was talking to a quantum scientist in Canada about this who said that he thinks we need a 10,000 qubit computer to solve the sort of interference problem, to get stable systems, to really have a breakthrough here. And today's biggest systems, I forget if it's 433, there was an IBM computer earlier this year, or I think I saw a headline of 1,000. So let's say best case is sort of 10-fold increase. Do you buy that? And what do you see as the biggest barriers getting to commercial viability?
Well, we are very biased so my answer will be very biased. We've been working on this for 7 years. I told you we thought it would take a decade. We're still on that milestone path. So that's a lot sooner than people thought. And the architecture that we're putting together is based on photons and photonics, and we get to use all the interconnects of fiber and all the packaging and silicon that we've done. So, excuse me. So I think it's closer in the mirror than you think. But that is a single vendor's pitch, because we've done it a different way. But you'll have machines that are fully error-corrected, running useful applications within that decade's time period.
Yeah. So let me just add to Stratton's answer. One, I think you're going to be very surprised by the progress PsiQuantum makes in the next 3 to 4 years. Just to double down on what you said, we have 65 years of knowledge of scaling in the semiconductor industry. We know, it's the only industry, in fact, who knows how to make trillions of something. Not just millions or billions, but trillions of transistors. And that technology is now being leveraged for, in the case of PsiQuantum, the quantum computer. That's the first point. The second point, to answer your question, is what we've learned on the GPU side is that it's not replacing quantum computers. We're not doing simulation of quantum computers. But these new NVIDIA and other chips from other GPU makers, by the way, every big tech company now is in the GPU game. Alphabet's making them, Amazon's making them, Microsoft's making them, everyone is in. Hopefully people here today can leave here and start a GPU company because it's very lucrative. But GPUs in large scale, 4,096 of them together, combined together, we can actually, using a technique called tensor networks, which comes from condensed matter physics, we can do really interesting risk management work, really interesting portfolio optimization work. It's not instead of the eventual quantum computer, but it's tractable today, it's doable today. So look for a multi-tool set. Don't be just focused on only one tool or one platform. Look for multiple tools in the toolbox.
We have time for one more audience question. Yes.
So in the public domain, we hear of thousands. You said millions. Are you disclosing where you are today in the form of like stable, coherent qubits?
We have no, because we don't. That's not our development pathway. Our development pathway is do the material science, which we are done with. We've done that. It's integrated, and we're getting tens of thousands of wafers and millions of chips from our Global Foundries, Skywater, and our other sources. So that part's done. The next part was to do PIC integration, which is photonic chips bonded to integrated circuits, right, to a long time. That is, and our packaging is done. The next part is to get into subassemblies, right? We have our first subassemblies have just come over the course of this quarter, and by the end or the middle of next year, you'll see all of that work done as well. Then all it is cabinets, power, and cooling. And our cooling, right, is cold. Right? It has to be 4 to 5 Kelvin. That's the same as a particle reactor today. In fact, we announced a few months ago, we're putting our alpha systems into SLAC, the Stanford Linear Accelerator, because their cryo cooling is exactly what we need. If you're doing superconducting qubits like IBM and Google, you need 10 millikelvin cooling. That's 1,000 times colder than what we need.
Colder than space.
Yeah, and there's no building on the face of the planet that has a 10 millikelvin big data room. Right? So our challenges are tractable, and we're into what my co-founder Pete says is concrete, steel, and fiber. Again, because we chose a direct, fast path to a big machine as opposed to intermediate steps, right? Which, in my opinion, are distracting and cost even more money.
Can squeeze a quick one in if there is a short question.
I think the other thing that I'm really passionate about that I always like to interject, and Jack's been a huge ally of mine, is just diversity. So, listening to everything today, we've made sure we've had a really diverse panel on every single panel set, which I really, really appreciate. But not just we're facing this issue in AI with the talent gap, but we're going to have it in quantum too. So one of the things that we're really, really passionate about is making sure that we bring diversity to the table in quantum with everything that we do. So as you're looking out there in your workforce and really leaning in for upskilling and everything, making those tools available to children, to elementary schools, but then also just to your workforce to really make sure that we are being as inclusive as possible.
And just to build on that, what's one critical takeaway I'd like to people have coming away from this is don't restrict the work in quantum in your bank, in your financial institution, in the innovation team. Love the innovation teams, love those folks, great people. But engage the cryptography people, engage the cybersecurity team, engage the CISO, engage the risk management team, engage the compliance team, engage the team, the actual markets desk. Right. So look at your whole bank when you think about getting ready for this kind of world. If you restrict it to your innovation team, I can guarantee you will have a failure, because the teams that really need to know what's happening will not be part of that conversation.
Great. And on that note, please join me in thanking my fellow panelists.
Thanks, Mandeep.
Thank you so much.